This ShowMe is about similar figures and scale drawings. Similarity is a key concept in applied geometry. The very earliest application of mathematics that we attribute to a single person was an application of similar triangles to the problem of judging the distance from a harbor to a ship out on a body of water. We credit the Greek philosopher Thales of Miletus with its discovery. You can read more about that and many other topics in my blog at Poliquin.com. We're going to compare similarity to the concept of congruence to make sure we know what it is to be similar. Then we're going to do 3 examples. The first is an abstract geometry problem like those at the heart of the work you'll do on similarity in a plane geometry course. The second is a classic problem in indirect measurement that I call the shadow problem. Finally, we'll touch on the use of a map as a scale drawing in a word problem. When we say that 2 figures are congruent, we mean that they are exactly alike in every way. When we say that 2 figures are similar, we mean that the appearance of one recalls the appearance of the other, but certain differences are allowed as long as they are of a specific nature. This table will clarify the part of that comparison that is the focus of our lesson. In congruent figures, corresponding angles are congruent. They have the same measure, and they appear in the same relative positions to each other in both figures. In similar figures, corresponding angles are also congruent. Again, they have the same measure, and again, they appear in the same relative positions to each other in both figures. As far as angles are concerned, then, congruence and similarity are the same relation. In congruent figures, corresponding sides are congruent. They have the same length and appear in the same relative positions to each other in both figures. In similar figures, corresponding sides are proportional. Each corresponding pair of sides creates exactly the same ratio. We call that ratio the scale factor. The sides of congruent figures will always be the same. The sides of similar figures will form the same ratio so that they can be related to each other in equations. An equation of ratios is a proportion, so we say that the sides are proportional. The ratio that results from each comparison is the scale factor. Let's take a look at how we use this idea to solve our 3 different kinds of problems. So here we have 2 similar trapezoids. Our mission is to discover the values of x and y and z. Now remember what similar means. All these angles in the corresponding positions have to be the same. So angle D is congruent to angle H, angle A is congruent to angle E, angle B congruent to angle F, and angle C congruent to angle G. So all those are the same. The sides, however, are not the same. They are proportional. Our first job is to identify a pair of sides that form a ratio that we can know, where both sides are actually known to us. Now, side DC corresponds to side HG, and both numbers are given. So, the relationship to between the sides of the larger trapezoid and the sides of the smaller trapezoid can be summarized in the ratio of those 2 sides' lengths. So, 7:3 is the key ratio for finding the 3 values we're looking for. In fact, this is the scale factor. every pair of sides, when you compare a side from the larger trapezoid to the corresponding side from the smaller trapezoid, will form this ratio. Let's work it out then. 7 to 3 has to be the same as the relationship between side BC and side FG. Well, we've given side BC the value of 5.6, and we decided to call, for the moment, side FG x. Now, in solving this proportion, we can use the cross product property of proportions. Take 7 times x, and that has to be equal to 16.8. Divide both sides by 7. X is 2.4. So 7 to 3 is the same as 5.6 to 2.4. X is 2.4. First problem solved. Now we're going to use that same ratio, that same scale factor, to find the other two sides. So we can erase the work we did to find x, and to do it over again for y. But this time, instead of using 5.6, the side corresponding to EF, which has a length of y, the side that corresponds to that has a length of 4. Same process will work here. Cross multiply 7 times y must equal 12. Divide both sides by 7. And given that these are lengths of figures, it's appropriate to go ahead and make these answers into mixed numbers. So y is equal to 1 and 5/7. Divide both sides by 7, you get 12/7, and 12/7 can be converted to a mixed number as 1 and 5/7. One last time then, we need to find the value of z. The process remains exactly the same. 7/3 is our scale factor, it's our known ratio. We need to continue to use it. So we're looking for z, and the side that corresponds to the side with a length of z has a length of 4.9. The same process again. Cross multiply 7 times z equals 3 times 4.9, which is 14.7. Divide both sides by 7. We discover that z is 2.1. So we have now solved for all the missing lengths of the sides of the smaller trapezoid. This is a very common problem, very common type of problem on standardized assessments, textbooks, and particularly in plane geometry courses, which American students typically take between their first 2 years of serious elementary algebra study. Here we have a classic, the indirect measurement problem that I like to call the shadow problem. We want to measure the height of the flagpole. We don't have the resources to do it directly, but we do have enough information to do it indirectly. The way this works is that we have to recognize that the sun's rays coming from a point so far away and from a light source so large come in at roughly the same angle for all locations near to each other on the face of the earth. Now, as a result, we can assume that the two triangles formed first by the sun's rays coming over the top of a flagpole and the ground between where those sun's rays hit the ground and the base of the flagpole, and then the flagpole itself, forms a triangle that is similar to a triangle formed by a human being standing nearby. And again, the sun's rays coming over the top of that person's head, and the side of the triangle that's formed between where the human being is standing and where those sun's rays hit the ground. In other words, if you look closely here, we'll mar the picture a little bit and show you that there are two similar triangles inherent in the setup of the problem. And there they are. And like I said, we're assuming that the sun's rays come in at the same angle for things that are close to each other on the face of the Earth. And that's a pretty safe assumption. Of course, the flagpole is erected at a right angle, and we're standing straight. And that means that the third angle also has to be congruent to the corresponding angle. Since all the angles are congruent, we've got a similar triangle. We've got two similar triangles. That means that the sides also have to be proportional, and that makes it possible for us to discover the height of the flagpole, even though there's no way for us to measure it directly. All we have to do is set up a proportion. Well, as in the trapezoid problem, the first thing we have to do is find two sides that have known lengths that we can use to make a scale factor. In this case, the two base values, 3 and 8, are the numbers we want to use. Then we want to also compare in the same way 5 and the height of the flagpole, which we call x because we don't know what it is yet. So, we need to solve this proportion. As before, we're going to apply the rule of cross products. Take 3 times x. We know that has to be equal to 8 times 5, which is 40. Divide both sides by 3, and x is 40 thirds. 40 divided by 3 is 13 and 1/3. So the height of our flagpole is 13 feet 4 inches. And that's how you can discover that without actually doing the measurement, as long as it's a sunny day. For our final application of proportions to scale drawings, I brought in a map of my home state of Kansas, here in the USA. It's a pretty large state, but I've never really spent much time considering just how far it is across the state. I've driven all over this state in my role as a sports coach. I've had to scout and go visit various places all around the state to help my teams prepare for competition. So I've been out into the nether reaches of the state, out to western Kansas, and driven across to Colorado from time to time for skiing. So I'm fairly familiar with how long the experience is to drive across the state at or just slightly above the speed limit. But I've never actually taken the time to note how far it is. So I'm going to make that measurement today indirectly using this map and the scale factor. As I've presented the map on my iPad, it's got a scale of 100 miles to 1 and 7/32 inches. So we're going to use that as a scale factor to determine the actual distance across the state. Now I've taken my ruler and measured from the eastern border to the western border already. As it shows on my iPad screen, that measurement is 4 and 15/16 inches. That's the distance from western border to eastern border in a straight line. Well, what I want to know is how many miles that is. So here we have two ratios. Here we have a proportion. Because this figure is supposed to be drawn to scale to the actual state of Kansas, which there's some assumptions involved in that. For instance, the state is large enough that the curvature of the Earth matters. Also, it's not really the same experience going east and west in Kansas. As you go west in Kansas, the elevation changes more than 3,000 feet as you climb toward the Rocky Mountains, which are still over the horizon, but nevertheless, you're on your way toward them as you head west. So that the western part of the state is nearly a mile above sea level, whereas the eastern part is 600 to 900 feet above sea level. Nevertheless, if you make the assumption that it's roughly comparable to a plane figure or a flat figure, then we can do this. So the proportion we're going to deal with here is 100 over 1 and 7/32. I'm going to go ahead and turn that into a fraction now, and that would be 39/32. That ratio has to be equal to x over 4 and 15/16. And again, I'm going to go ahead and turn that into a fraction, to an improper fraction now. So that will be 79/16. Solving this, of course, involves cross-multiplying. 100 times 79/16 has to be equal to 39/32 times x. Of course, our goal is to get x by itself and find a statement that says x is something. To accomplish that, then, we would still have to do 100 times 79/16, but then you'd have to divide that by 39/32, which means you're going to multiply by the reciprocal, which is 32/39. Well, we're getting into pretty arcane territory for fractions, so it's time to turn this over to a calculator and get a reasonable decimal approximation, since I am not bound and determined to know exactly how far it is from border to border, and in fact, this isn't the right method for doing that anyway. So, turn to the calculator, and we take 100 times 79 times 32, divided by 16, divided by 39. And the result is approximately 405 miles. So that's how you would use the scale factor on a map to discover a distance, using a measurement you also made on the map. So these are the basic applications for similarity in scale drawings. They're very important to understand, especially if you plan to go into any kind of work where precision representations of things are important, where it's important to have a drawing that really does have a lot in common with the final product or with reality. Surveying, map making, cartography, but also any other kind of mapping or representation of something in 2 dimensions. Engineering, drawing, drafting, architecture, all of those applications are going to make frequent and constant use of similarity and scale drawings. It's going to be very important to know how to work with them to create proportions and calculate information that you need from a picture. Hope you found that useful. Again, there's more details about this and other topics at my blog at MikePoliquin.com.